Okay, so we will start now. So sorry for the delay and for the problems. So thank you for participating in this in the first symposium of the Central Volcanic Zone of the Andes in this virtual format, which is organized by the Universidad de San Andrés of Bolivia, the Instituto Geológico Minero y Metalúrgico INGEMET del Perú, del Observatorio Vulcanológico INGEMET, por el IGP, el Instituto Geofísico del Perú, por la Fundación Miguel Lillo, perdón, de Argentina, y también por la Universidad Católica del Norte, específicamente por el Núcleo de Investigación en Riesgos Volcánicos Ckelar Volcanes, which is also supported by the YAPSEI and ALVO. So thank you for participate in this meeting, and now we will present the keynote speaker for this day, and after that of this presentation we will have two rooms. The room number 1 will be this, and the other one is the room number 2, where we have different presentations or different talks about the volcanic hazard and risk, and also about of the geophysical applied to volcanism and also to volcanic monitoring. So, Pablo.
Okay, thank you, Gabriel. Good morning or good afternoon, everyone. Thanks for being here. We have the great pleasure of welcoming Dr. Susan Kay for the keynote talk today. I'm sure she really doesn't need much of an introduction. I'm sure everybody here knows her, has read many of her papers, so I'll be very brief, also because we're running late. Dr. Kay is a professor at Cornell University in the US. And well, as you all know, in the last few decades, she has been working, researching on basically on the trying to understand the evolution of the continental crust and the magmatic processes that go in there. In several magmatic arcs, including the southern Andes, Aleutians, for example, and of course the central volcanic zone. I think her work is really has been a fundamental or a framework for all of us volcanologists to try to understand what's going on below and how magmas evolve and eventually erupt and form volcanoes. So it's really she is a fundamental researcher for most of us. So it's a great pleasure to have her here. And so, yeah, I think I'll give the floor to Susan. Go ahead, Susan, whenever you're ready.
Okay, share screen. Oh. But now I don't see the presentation.
Yeah, now we're seeing again your desktop, but not the PowerPoint.
There, do you see it now?
There we go. Yeah, great. Perfect.
Okay, so I'm going to talk about the Southern Volcanic Zone and the Puna back arc in the southern part, really around 24 to 28 degrees. And I'm going to talk about a magmatic perspective linking geochemistry to seismology from the slab to the crust. And I'm not really a geophysicist, although I spent my career at Cornell surrounded by geophysicists and have been indoctrinated in geophysics and gotten much more interested in and become involved in some geophysical experiments in the Andes. So I trust much of the interpretation of my colleagues. Okay, so this is a picture of the Incapijo Dome in the southern Andes. This is a seismic image from Ward et al. Paper showing only the crust, but showing a deep magma, possible magma chamber. Okay, so the region I'm going to talk about is essentially this region in the black.
Sorry, Susan, but now we cannot hear you. So
I'm muted. Oh, am I
yes.
unmuted?
Now all good.
Muted. How did I get muted?
Yes,
Mute.
now we can hear you. So no, again.
Now can you?
Yes.
Okay.
Okay, thank you.
Yeah. Technology is terrible. Okay, so I'm going to talk about the area in the black box here. It is the southern part, most part of the southern volcanic zone. And the picture we just saw of Inca Pijo is right here. It's the last active center in the central volcanic zone, and just north of the flat slab. And we're going to talk about, unfortunately, it's covering up my screen. Well, the chemistry and age of the arc magmatic rocks with seismic images. And is there any way to remove all the images? I can't see my text on my screen.
Oh, I don't know, but we can see your presentation. So
Yeah, but I can't.
ah, okay.
Sorry, Susan, what are you seeing?
I'm seeing, but all the people are on top of my presentation. I see only half of the presentation.
You can like minimize the people or the participants, or just move the box away, the window.
Yeah, it won't move. Oh, what a disaster. Jesus Christ. Well, I can't.
There should be a button up in the upper right, which tells you how to split up your screen between people and the presentation, and you can choose just a speaker. There's a different sort of layouts of your screen.
Yeah, you know, I know that, but I don't see it.
It's in the upper right in my Macintosh. Upper right on your screen. No, it should be in the Zoom.
So now you're not seeing my.
We are seeing it.
We're seeing your PowerPoint, but not the Zoom window.
Not this.
Within the Zoom window,
just your PowerPoint.
Can you see that?
Yeah.
Yes.
Will that work?
Just make it as big as possible.
Can you see that?
Yes.
Okay. So, sorry for all the confusion. Let's talk about the distribution, chemistry, and age of arc magmatic rocks combined with seismic images, which are powerful tools for understanding the volcanism and reconstructing the thermal and material balance of the central Andes. And as I said, we're going to focus on the area in the box. There's a number of regional factors consider in interpreting magmatism, and this has more to do with the tectonics and the slab. And so I thought I would list this. And okay, the first is the age and influence of the entire subductive slab region, the surrounding mantle conditions, and the degree of penetration of slab into the mantle. And this is something that now with all the new tomography and all of the dynamic models, all of a sudden people are worried about how far the slab is penetrating into the mantle and how that's influencing characteristics of the subduction zone. And then the second, of course, is the angle of the subduction and the shape, thickness, and age of the subducting slab, the role of forearc subduction erosion, And I put relamination in quotes if it occurs. There are a number of papers now that are pushing relamination in the Andes, but there are problems with the massive amounts of relamination that some people are talking about. And then we have to consider plate motion, convergence rate, relative slab advance or retreat. So whether South America is moving, how South America is moving relative to Nazca. Properties of the upper mantle and crust underlying the magmatic center, and the relative amount of crustal gain or loss, lithospheric delamination. So these are some of the themes. Okay, so talk first about the impact of the subduction history, and there was a very interesting paper that just came out by Rodriguez et al. In 2021 on S-wave tomography, and showing in the northern Puna, the southern Puna, and down into the flat slab, and this is also goes up into Peru. There appears to be a low velocity region under the slab, just immediately under the slab, and the slab is not very well imaged. And then as we go into the southern Puna, the southern part of the Puna and the northern part of the flat slab, there's a near vertical high velocity zone in depth southwest of the slab that people have been, what is this? Is this a formish slab? How does this connect with the present slab? And most of these images don't have much resolution, about 300 kilometers. So the resolution is 300 to 1200 kilometers. And then this is not with the Puna Altiplano, but when we get down into the Chilean flat slab, there's actually a gap in the slab. There seems to be a tear in the slab. And the age of this tear, the question is the age of the tear. There is volcanism in the San Luis region as old as 10 million years. So there seems to, it's much more complicated than just the shallowing subduction zone when you get into that region. Okay, so going on, we'll talk about the Juan Fernandez Ridge, and Sean showed this figure the other day. It's out of our paper. It's based on some things that we did in 2009, but a much more beautiful picture. So the path thickness and angle of the aseismic Juan Fernandez Ridge. And the ridge approached from the north and began subducting in the Miocene. And then 45-degree northeast trending segment swept southward, progressively producing shallowing by steepening, followed by steepening that has long-term implications for the central volcanic zone arc and back arc magmatism. And then finally, this 80-degree northeast trending segment began subducting at 11 to 10, creating magmatic quiescence over the modern Chilean flat slab region. So if another figure out of the De Silva and K paper, showing the history is recorded in the magmatic anomaly patterns, the distribution and chemistry of the magmatic centers, and the features in the seismic image. So these are some cross sections of receiver function image with Rayleigh wave dispersion data from ambient noise tomographic images for the crust from Ward et al. 2017 and Delph 2016. So they also reflect the history. So we can try and figure out the history from the magnetic anomaly, the distribution chemistry of the magmatic centers, and the features in the seismic images. So these are the images from south to north. This is the Inca Pijo caldera that I showed at the beginning. Then we go up through the Incahuasi. Why he called it the Incahuasi anomaly escapes me, since the big feature there is Ojos del Salado, but that's a minor point. Then going further north, we come into Galan. Then further north, La Zoufre, and finally the APVC that Sean talked about. Now in these images, anything over velocities less than 2.9 are considered by them partial melt, with plutons from 2.9 down to about 3.6. And so the plutons are interesting because, as those of you who've worked in the Andes for a long time know, that all the plutons are not young. There seems to be some correlation of some of their plutonic rocks which enjoy the Ordovician. So you can't attribute all of the plutonic rocks to modern Andean processes. So we'll be looking at these images and comparing them to some other seismic images and other figures. Okay, so this is from a paper in 2009 and 2010 work that we did with Betty Koya, and a compilation of all of the ignimbrites of the Puna. And at that time, we thought that they basically young to the south, but now, thanks to the work of Guzman and others, we know the Cunha Pampa and the Luingo are 13 to 12. So the situation isn't quite as simple as depicted here. And we also know now that even down in the flat slab, we had magmatism as old as 14 to 12 million years. So the picture is more complicated than when this was, but basically it's still relatively associated with the shallowing and steepening, the subduction bone. But you realize, particularly when you get to the south, the picture is more complicated and there's many things we still don't understand. Okay, so we're going to concentrate then on this region in the red box here. Here's Cerro Golan. And we came up with this series of cartoons, essentially looking at what was happening in time. And so starting there was a change in relative plate motion of South America versus Nazca, and the Puna went into compression around 16 to 11 million years, and in this area the slab shallowed. So the slab shallows and the crust thickens from 16 to 8 million years. Then there's a period between 7 and 3 million years where at least in the central volcanic zone, the arc stepped some 50 kilometers to the east. And we have attributed this to being associated with subduction erosion. And so that's why there's a box here showing a 50-kilometer displacement of the position of the trench. And then after that, the slab steepens. We get the ignimbrite flare-up, the Golan ignimbrite, the big ignimbrite. And then at this time, we inferred delamination. And this was to explain the characteristics of the mafic rocks. And so this was all basically deduced from using the geochemistry, the distribution of the volcanic rocks, and comparing it to geometry of subduction zones. And so in order to test the picture that we drew here and the delamination and what the geophysical implications, there were really no geophysical data in the southern Puna. I guess I instigated the project, although I'm not a geophysicist, and there was a group from Cornell, Eric Sandvall, the group from Potsdam, and we put in 75 seismic stations, which are shown by the squares, and the earthquakes that were recorded and used in making the images that I'm going to show you are the circles here, and they're coded by depth. And you notice that I'm the last author on this paper. Everybody else on here is a geophysicist, so I defer to them in terms of the geophysics. Okay, so we're going to look at 3 profiles across this, the P2 line, the P3 line, and the P4 line. There's another line up here, P1, that basically is, at least for the purpose of this talk, similar to the P2. Okay, so this shows the location of the P4 and the P3 line. The P4 line goes through, those of you who have worked in the southern part of the Central Volcanic Zone, and many others will recognize the names of these centers. There's a Copiapó. The first line goes just south of Ojos del Salado. The Incahuasi is here. So Tres Cruces, Ojos del Salado, Incahuasi. And the second line that is further north, and it goes essentially through Peñado and Cerro Blanco and further east. So we're going to look at these lines, and then later on we'll look at the 2 to the north. Okay, so this is the P4 line, and the upper image is the geophysical data. The second is the interpretation. And you can see that if we locate Tres Cruces would be here, Ojos del Salado here, Incahuasi, and this would be Copiapó, and Ferrejón Negro way out to the south, out to the east. And so and these are the earthquakes, a tremendous number of earthquakes. So the idea is that the earthquakes generate the melting, and so you have sort of fluid release associated with the slab, and that this path here shows the melt migration, which starts at depth, and then the peak of this, the peak here is Incahuasi on one side, Ojos del Salado in the middle, Tres Cruces, and surprisingly, the very low velocities around the region of Copiapó. The Copiapó volcano, where the youngest, at least the youngest ages, are 6 to 7 million years. So, and then this is the subducting slab, and this is the area. It's in this area between Copiapó and Ojos del Salado, where the arc migrated 50 kilometers at 7 to 3 million years. And the question is, if there was forearc subduction erosion, is any of this material still incorporated in the mantle? Is it still caught here? And so very speculatively, because the high velocity material goes so high, the question is there any of that removed crust? Because the arc is now here, the arc moved from here to here. And then the profiles at the right are the images of Delft at the same scale. And one thing you should notice, like everybody is using these Delft and Ward images, but notice that the crustal thicknesses shown here is like 50 kilometers, and here they show 60 kilometers. And so this is, they really didn't have the resolution in the type of geophysical data they have to really define the mojo. So you have to be careful of the mojo as that are defined in those images. The mojo here is defined by essentially receiver function images. And so place the mojo somewhat shallower, 50 kilometers rather than 60 kilometers through this region. And then this is the P3 line. Here's Peñado, Cerro Blanco, Karachi Pampa, which is more in the back arc and one of the mafic flows. And so this, now the low velocity region is more concentrated between under Cerro Blanco and actually extends towards Karachi Pampa. And oops, the big low velocity zone that was under Copiapó is not present. So, and again, there are some high velocity chunks that we didn't know how to interpret. And again, the question is this some sort of crust removed by the lower crust, eclogitic crust removed by boric subduction erosion? And again, this is the Delft image, just for comparison. Okay, so going to we published a paper in 2013 where we summarized all the chemistry we had of this region, and these images are from these 2013 papers, and this is just the samarium ytterbium, which is an indication of the presence of garnet. You can see that as we go from west, from Tres Cruces, through Ojos del Salado, through Incahuasi, that even though the crustal thickness is similar, we see decrease in the samarium ytterbium ratio. And also that Inca Piju looks very much like Tres Cruces. So Tres Cruces is essentially in the forearc. So this would be, and essentially Tres Cruces. Okay, so now moving northwards, we have the two lines going through the Cerro Galán region. We're only going to talk about the P2 line because the P1 line essentially goes through the northern tip of Cerro Galán and the Salar de Hombre Muerto and shows some of the similar features. There are differences, but we don't have time to discuss it. And so the profile, the next profile is this one. And so this profile is to test for the delaminated block that we had proposed, the delamination, the shape of the subduction zone. And so essentially, and so we're going to look at the geochemistry that we used to propose the shallowing of the subduction zone and the delamination, and then the steepening. So we had shallowing up till 7 to 3 million years, then it started to steepen, and we showed delamination of a block and the formation of essentially the ignimbrites. And so just looking at the lanthanum tantalum ratio as a measure of slab input. So if you look at this 25 to 16 million years, relatively steep slab, the lanthanum tantalum, which is in some ways a measure of the arc component, is highest at the arc front. From 14 to 7, it increases in the back arc as the slab shallows. And then less than 7 million years, it again steepens following the delamination. And the samarium ytterbium as a measure of crustal thickening. So the samarium terbium ratios go over 4 after 7 million years. And so between 7 and 4 million years, requiring a garnet-bearing residue is attributed to crustal thickening. Now, I know that there's been a lot of discussion about when the crust thickened in the southern Puna. Some people have the crust thick all the way into the Eocene, but at least in terms of shallowing of the subduction zone and some of the deformation and the chemical signature would suggest that there was additional crustal thickening in the Miocene associated with the shallowing subduction zone. Okay, so then moving from a general view into the general area of the Cerro Galán region. This is where all these mafic lavas in the southern Puna that I guess that have been the subject of much interest for many years. And it was in our 94 paper looking at these lavas that we first proposed delamination underneath the part of the mafic lavas that have a more interplate-like signature. So you have mafic lavas to the south, mafic lavas to the north that have more calc-alkaline signatures, but then you lose this calc-alkaline signature, particularly in the rocks under the mafic lavas under 4 million years in the central region just in front of Cerro Galán. And so it was in this region that we suggested that there was a delaminated block, and then there was a ignimbrite flare-up, which produced the Cerro Galán. And okay, so if we look at lanthanum tantalum as a signal of this delamination, so this is all of these mafic rocks, the whole region, from 7.5 to 4 million years, and they have an arc component, lanthanum tantalum, suggested by the lanthanum tantalum ratio. And then after we go less than 4 million years, we see division, and this is the from the Pasto Ventura to the south, Hombre Muerto to the north, and this is this center segment. So here's Hombre Muerto up here. We maintain the calc-alkaline signature. This is to the south, we maintain that calc-alkaline signature, but we lose that and the rocks become more interplate-like the mafic rocks in this central region. So it was under this region that we suggested that there was a possibility of a delaminated block, which then removed the lower crust and lithosphere and produced, as the slab steepened, the heat came in and creating the Cerro Galán ignimbrites. And if you look at this is a compilation of all the ages that I know of for the ignimbrites and the mafic lavas. This is the Cerro Galán complex, greater Cerro Galán complex, and the mafic lavas. There's an interesting pattern that you have mafic lavas followed by an eruption, mafic lavas followed by eruption, mafic lavas followed by eruption, mafic lavas followed by eruption with the youngest age of Cerro Galán at 2.1 million years. And now we have mafic lavas again that are 1.5 to, I put 0.2 question because they're almost too young to resolve. So in this cycle. Okay, so here's the image for that Cerro Galán region. Again, this is the cartoon, and this is the actual geophysical image. And in this region, we, after 4 rounds of reviews and much discussion, finally convinced all of the reviewers that there actually was evidence for a high velocity block underneath essentially the western side of Galán, which essentially would be underneath this region right here, where the interplate-like lavas are. And so the delaminated block, and then this is would be the Cerro Galán low velocity material under Cerro Galán. All right, the other thing to notice here is that we have, this is again from receiver function data and the work of actually Yuan, arguing that the crustal thickness underneath Cerro Galán is like 50 kilometers, 40 kilometers, and that actually,
Sorry, Susan.
yeah.
I'm very sorry to interrupt, but I'm being told here that there's a problem with the connection, the Zoom connection. For some reason, the premium account, which they have there in Chile, is not working. So it's gonna cut in just a few seconds. So just please, everybody, reconnect to the same room, and we begin from there. It's gonna disconnect.
The modern origin and destruction of continental crust, and stop there, and sorry for all of the interruptions.
Thank you so much, Susan, for your talk. So this was a great talk, and sorry all the people for all this problem with this connection, and also with for this problems with the screen. So Susan, thank you for your talk again, and we have some questions. So I don't know if you can see the chat, because Modesto Portilla has a question for you. The first one is, what physics process does give origin of the delamination for the subduction slab?
Geez, I can't see it more. Maybe if I get out of the presentation and then I can see the chat. I really,
Yeah.
Let me just get out of the presentation.
Mm-hmm.
No, now I don't have the chat.
Okay, I'll don't worry, Susan, I can read them out to you.
Okay,
if you want.
why don't you read out the questions?
Okay, so yeah, the first question here is from Modesto Portilla Gamboa. It's two questions actually. First one, what physical process gives origin to the delamination from the subducting slab?
Oh, well, the delamination is a gravitational instability of the essentially dense lower crust and lithosphere. So essentially eclogitic, it's denser than the underlying mantle, so that it detaches. And also it's very important that it occurs when the subduction zone is steepening. So there's a path essentially for it to drop off. So it's a density argument. If you're interested, there's a whole series of papers, but the whole lithospheric delamination and argument is based on density, that it becomes eclogitic, becomes denser than the underlying mantle, and delaminates.
Okay, thanks. And the second question is, are the earthquakes produced by the aqueous fluid migration, or would it be the other way around?
Well, you mean the slab earthquakes?
Yes, I think so.
Well, they're associated, it depends on, which geophysicists you follow, but associated with the eclogization process. So essentially dehydration and the density change produces the earthquakes. So the dehydration of the slab is associated with the eclogization, and the earthquakes. At least that's the argument.
Okay, great. Thanks. If anybody has other questions, they can type it in the chat and I'll read them out, or you can raise your hand and you can ask directly. Okay, in the meantime, I'll have one question. I saw in the slide about you showed like a cycling, very interesting cycles of mafic volcanism followed by ignimbrite. So now you in the last one, the present one would be a stage of mafic volcanism. So doing some futurology, you would say that we are heading towards a new ignimbrite eruption in the future. That's well one question. And also, would it be possible to say where would be more likely for this future ignimbrite eruption?
Okay, well, I mean, that's a difficult question since I can't see the future, but in the process of our seismic experiment, we did see a couple seismic swarms on the Golan caldera, in the middle of the caldera. So there is some active seismic swarms, and because there's not a permanent seismic network there, the network was out for essentially a year, and now there's actually no good monitoring of this region. There's no seismic network that you would see those seismic swarms. So we saw a swarm essentially in the center of the Cerro Golan caldera, and then the other swarm was west of Cerro Blanco. But if there, well, I don't know. I mean, I would suggest that it's probably unlikely that there will be another major eruption of Golan, just because the shallow subduction zone has moved to the south, and the conditions are not what you would expect. And I think that's what most people would say, that they would not expect another mega eruption of Cerro Golan, but it doesn't mean there could be a smaller eruption. I hope that answers your question.
Yeah, yeah. No, I know it's just yeah, it's
I can't see the future.
Really to say, but yeah.
But yeah, it's interesting, the pattern. I was actually surprised when we compiled all the ages, and I don't know if there's any more. We did this with Betty Coy about 6 months ago. I don't know if there's more unpublished ages, but yeah, it's an interesting pattern that the mafic lavas, and so maybe a smaller eruption of Cerro Golan, and that depends a lot on what the magma volume is, and that becomes a question of, you look at the models of Delft and you look at our P-wave tomography. I mean, how much meld is really down there? I think that the seismic data is not sufficient in this region to resolve these issues. It'd be interesting to go put a network and actually do it in even more detail. There's no permanent seismic station. It's the only time there was ever a network across most of this region, and it was really fairly short time. So we don't have control.
Okay, great, thanks. If I don't see other questions, anybody?
Yeah, I had one. Excuse me. Gerhard Werner speaking.
Yes, go ahead.
Okay. Sue, in one of your last slides, you showed the tomography and then these circles showing where potentially there was delamination. Now, what I observe is that in one delaminated area, you have a red dot in the north, and then the others further south, they are more associated with blue dots. Now, what is the depth of the tomography layer there, and how could it be that delamination occurs where the P-wave tomography shows different perturbations?
Well, that's because the delamination would have been older to the north, and the block would have moved. The idea is the block has been removed because the block doesn't stay there. There's a circulation in the mantle. So in the north, essentially in that Beck and Zant area up in southern Bolivia, the block is moved out of the picture, and you have to think about how long it stays, the circulation of the mantle, and so that means that at least under Cerro Golan, it's recent enough that it's still, the block is still there, and that's up under Coranzuli and certainly Tuesday, because Tuesday is essentially still active. So you have to factor in the mantle flow pattern.
Okay, I see. But in the south, then you have your alkaline or your interplate signatures right there. But in the northern dot, where you have the red blob right centered on the delaminated area, Is there any age information when this could have been eliminated? And is there any alkaline interplay type volcanism sort of focused in that area?
No, I don't know of any alkali. You know, the magmatic story is obviously the best in the southern Puna.
Yeah. But you would expect the same thing happening.
And that's the interpretation of Beck and Zam, and it's just basically based on missing lithosphere. I mean, you know, it's based on crustal mantle profile, and there's a big hole there. So.
Okay, thanks.
Okay, thank you. We had another question from Patricia McQueen. Is she still there?
Yeah, this is from Cornell.
She raised her hand, but now, oh, there we go.
Yeah, sorry, it was briefly not allowing me to unmute myself. Thanks for a great talk, Dr. K. I was curious about the relationship between the ignimbrites and the mafic volcanism. Are they genetically related, or is just kind of one precede the other, or the mafics from the mantle and the ignimbrites are a result of heating and then erupting something that's in the crust, or how are they related?
Well, I mean, the mafic lavas indicate melting of the mantle. So the question, I guess the question is, let's see if I can get back to the, well, I can't get back to the figure. I guess you can't see the figure anyway, right? No.
No, we see your PowerPoint now. Yes.
Yeah, I mean, the mafic lavas are associated with the heating that's producing the ignimbrite. So essentially, if we go from the mantle to the crust, you have you have to have a heat source to produce an ignimbrite. So the mafic magmas are the heat source, and so they precede and then evolve through the crust, because the ignimbrites erupted from much shallower depths. So the mafic lavas are associated with production of the ignimbrites. Remember, the ignimbrites are half crust and half mantle, and so they're involved with a lot of crustal, say up to 50% crustal melting. The calculations have been done from oxygen isotopes, as Gerhard knows well, would suggest about 50% crust. So the mafic magmas producing the melting in the crust, which leads to the production with the crystal fractionation of the ignimbrites, which then are stored at shallow levels before they erupt. So there's a connection. The mafic magmas have to come first. Does that make sense?
Okay, thank you. Any other question? I don't think so.
Yeah, I don't think I didn't put in that cross section of the what's happening through the crust, because Sean showed it the other day, and I thought that I would emphasize more than some of the geophysics. So I don't have that in the presentation.
Okay. Okay. So we'll be finishing up, I guess. Thank you very much, Dr. K, for your presentation. It was great. And again, sorry for the inconvenience.
I'm sorry
with
for
the technical details.
Sorry for the technical problems of my screen share.
No problem. I'm being told here in the chat, you will see a new link, Zoom link for room number 1 for the rest of the day. It seems it has been solved, but with this new link. So right now we will disconnect from this Zoom link, and people who want to go to room number 1 should use the new link that's in the chat. And people who want to go to room number 2 use the original number 2 link, which works okay. So see you in any of these 2 rooms. And thank you very much. And thanks again, Dr. K, for your presentation.
Volcán explosivo, ¿no? También puede tener emisiones de caída de cenizas un poco leves, como también fuertes, como ocurrió hace 2050 años. Y tenemos software de simulación que estamos usando a la fecha. Por ahora estamos concentrados en los que es lajares, plásticos y caídas. Vamos a terminar de culminar estos peligros y vamos a seguir con los proyectiles balísticos, flujos de lava y etcétera. Y acá les presento los software de simulación que estamos utilizando. Hay que considerar de que el Observatorio Vulcanológico del INGEMET ha realizado una serie de mapas de peligros. Por ahora tenemos 7 volcanes, del Misti, Ubinas, Ambato, Sabancaya, Tixani, Yucamani, Tutupaqui y Sarasara, ya realizados, y estamos a tiros del Misti. También estamos realizando el del Huayna Putina, el mapa de peligros, y del Chachani. Bueno, concentrándonos en lo que es el Misti, ¿no? El volcán Misti es uno de los volcanes más activos del sur del Perú. Se ubica en la zona de Arequipa. Arequipa es considerada la tercera ciudad con mayor riesgo volcánico en el mundo. Tenemos más de 1.300.000 habitantes alrededor del mismo, ¿no? Entonces, bueno, este volcán se ubica justamente en la zona volcánica de los Andes centrales. Como les había explicado preliminarmente, nuestro mapa de peligros que tenemos desde el 2007 presenta esta parte que es el mapa de multipeligros, ¿no? Y justamente, bueno, esta es la zona de alto, moderado y bajo peligro. Este mapa se ha realizado con el software La Jarceta, con algunos, el cono de energía, utilizando la técnica del cono de energía, que también es el principio de La Jarceta. También hemos utilizado mucho lo que es la geología, pero ¿cómo es que sirve la geología para poder calcular o poder realizar este tipo de mapas? Dependiendo hasta dónde han llegado los depósitos, el alcance de los depósitos, la extensión de los depósitos, es como que calibramos nuestra simulación, ¿no? Para ello tenemos que hacer varias simulaciones con tal que calcen a la realidad. Y obviamente es una parte fundamental ir al campo y poder corroborar dónde hay estos peligros, si es que efectivamente esta zona ha sido afectada por un determinado peligro como tal. Entonces, bueno, esto es lo que se puede mostrar aquí. Y también tenemos mapas de peligros un poco focalizados, como les comentaba. Este es en cuestiones de la caída de cenizas. Este es para una erupción de magnitud baja, de índice explosividad 2, y magnitud de moderada grave, de índice explosividad 3 a 6. Hay que considerar de que estos escenarios eruptivos son muy importantes de considerarlos, de caracterizarlos, debido a que, como les comenté anteriormente, este volcán ha tenido erupciones de moderada explosividad, pero también erupciones grandes, ¿no? De índice de explosividad 2, incluso hasta 5. Y por el otro lado, el mapa de peligros por flujo de barro, huaico o lajares, ¿no? Bueno, en este caso son terminología que lo vamos a ir actualizando, como ustedes ya lo han podido apreciar, todas las cosas cambian, más específicas, ¿no? En este caso tenemos unas simulaciones que se realizaron con el Ajarceta, utilizando estos volúmenes que pueden ver ustedes aquí, y también con la metodología HL del cono de energía. Pero acá lo que estamos proponiendo realizar es un poco más a detalle estos mapas de peligros. Por otro lado, presentarles también que este mapa de peligros está en una plataforma 3D. Justamente ustedes entran en la web a GeoCatMin y pueden acceder a volcanes 3D y visualizar al volcán Ubinas, al volcán Misti, al Sabancaya y al Tixani. Esta metodología la hemos usado justamente para que las personas, la población pueda sumergirse ahí en el mundo tratar del 3D y poder visualizar de una mejor forma dónde están sus viviendas, centros educativos, hospitales, si están en una zona alta, moderada y baja, ya que hemos actualizado también la ubicación de las instituciones que les acabo de comentar, ¿no? Considerar de que este es un inicio, también nosotros presentamos o tenemos la intención de poder acoplar la realidad virtual también para que sea más didáctica nuestra presentación de los mapas de peligros. Bien, entonces paso a la parte de justamente los avances que tenemos con la actualización del mapa de peligros del volcán Misti. En esta parte, explicarles en que desde el 2007 hasta la fecha no se había tenido la actualización de este mapa. Sabemos de que es bueno siempre actualizar este tipo de mapas, este tipo de información, debido a que la tecnología cambia, los modelos de elevación digital, las resoluciones de mapas bases cambian y se vuelven más detallistas, ¿no? En este caso, nosotros hemos elegido ello justamente para poder tener un mapa por peligro eruptivo, por peligro emitido por el volcán Misti. En este caso, se muestran, por ejemplo, polígonos de color azul, donde estamos utilizando para el mapa de peligros de lajares, la relación un poco para hallar el volumen de cada quebrada, es decir, el lajar que puede emplazarse en cada quebrada. Para ello, hemos delimitado microcuencas por técnicas de hidrografía con el Divorcium Aquarium, ¿no? Y en esta parte es que hemos podido determinar los puntos de inicio de los lajares, ¿no? En este caso, hemos buscado estas microcuencas. Por otro lado, hemos visto también por conveniente que si bien es cierto se pueden generar lajares en la parte superior, pero también mientras va descendiendo por las quebradas se van alimentando, ¿no? Entonces, también hemos propuesto realizar polígonos un poco más alargados, donde confluyan 2 o más quebradas. Considerar de que el mapa de lajares, bueno, las simulaciones que estamos considerando 60% de agua y 40% de sólidos, ¿no? Eso debido a que nuestros depósitos presentes en los alrededores del Misti justamente tienen esta fracción. Y en base a las precipitaciones pluviales es que hemos podido calcular esos volúmenes por quebrada. Bueno, esta es una imagen desde el puente Bajo Grau, del puente Grau hacia el puente Bajo Grau, ahí en la zona muy cercana a la Plaza de Armas de Arequipa, la zona central, donde podemos ver que justamente el río Chili se desborda, más o menos es por esta parte, ¿no? Estas son las precipitaciones pluviales que estamos usando hasta la fecha de 30, 50 y 124.5 milímetros. Estas precipitaciones lo hemos tomado en base a la base de datos que hemos obtenido del Cenami, ¿no? Justamente este dato es una de las precipitaciones más altas que ha sufrido la ciudad de Arequipa. Hay que considerar también de que el Misti tiene a veces, bueno, tiene una cobertura de hielo que no es permanente, generalmente a veces se extiende cuando hay corrientes de frío, cuando no, las temperaturas bajan, pero de todas maneras esa pequeña capa la hemos considerado también en el volumen total que estamos teniendo para los lajares, ¿no? Esta es un poco la información que hemos utilizado, ¿no? De diferentes volcanes que son parecidos, que también están dentro de la zona volcánica de los Andes centrales, y para poder determinar los inputs. Hemos utilizado 2 software, el AjarZ, ¿no? Justamente en el AjarZ hemos podido determinar estos volúmenes en total, 1.5, 6 y 11 millones, justamente que calzan a alto, moderado y bajo peligro. Y esto es más o menos una simulación preliminar, ¿no? Acá falta afinar muchos detalles sobre cómo quedaría el mapa de lajares específico utilizando estos volúmenes, ¿no? Un poco actualizados. Y por otro lado, también estamos utilizando el apoyo aquí de unos colegas que usan el Volflow, un colega que usa el Volflow, estamos tratando de hacer algunas simulaciones, justamente empleando este código y utilizando los parámetros, los inputs que hemos ido recopilando con las diferentes bibliografías que hemos realizado en base a esta actualización de información, ¿no? Y también nos hemos guiado por algunas simulaciones, como les dije, unas calibraciones para poder ver cómo es que se actúan, cómo es que se asemeja más al detalle. Por otro lado, estamos realizando la actualización del mapa de peligros con respecto a los flujos piroclásticos también. Esto recién lo hemos empezado hace poco. Hemos caracterizado, en este mapa se ha separado todos los depósitos de flujos piroclásticos. Primero hemos empezado con los de pomis y ceniza, ¿no? Los de colapso de columna eruptiva. Para ello hemos revisado bibliografía de Harpel, de Coveñas, de Charbonnier también, ¿no? Tanto para lajares como para flujos piroclásticos. Hemos podido determinar que sí, efectivamente, los flujos piroclásticos alrededor del volcán Misti son tienen bastante volumen, representan a erupciones con alta explosividad, ¿no? y hemos podido calcular algunos volúmenes. Si bien es cierto, hemos tomado a la fecha, justamente Charbonnier hizo un estudio en el 2020 acerca de los depósitos de flujos piroclásticos de pómez y ceniza, de bloques y ceniza de la erupción del 2000, y en base a eso, sumado también con otra información que hemos ido recopilando de otros volcanes, como pueden ver aquí,